Good morning, everyone. Today's topic is lasers. First, we'll discuss what are the contents which I'm going to discuss here. Lasers, introduction, characteristics of lasers, spontaneous emission and stimulated emission of radiation, or interaction of radiation with matter, population inversion, pumping methods, ruby laser, helium neon lasers, semiconductor lasers, and applications of lasers. Now, first coming to the introduction part. The word laser is an acronym that stands for light amplification by stimulated emission of radiation. Light gets amplified. Light means we are taking a ordinary light and we are amplifying that particular light through the mechanism called as stimulated emission of radiation. There are two types of emission processes are there, Rama. The first one is spontaneous emission process. The other one is stimulated emission process. Laser follows the stimulated emission process to produce the uh, laser light to increase the amplitude of the light. Next, lasers having some essential properties like high directionality, high intensity, high monochromaticity, high coherence, etc., etc. Next, the stimulated emission process was first postulated by Albert Einstein in 1917. Next, in 1960, the solid-state ruby laser is developed by Dr. T.H. Maimon on this principle on using the Albert Einstein principle that is called as stimulated emission process. By using stimulated emission process, the first laser was introduced by Dr. T.H. Maimon, which is called as ruby laser. Next, but this particular ruby laser is a pulsating laser, not a continuous laser. It does not produce the continuous laser beam, but it produces the pulsating laser beam. For that, to produce the continuous laser beam, Hari and Javan and his collaboration developed another laser called as gaseous laser, which is made up of helium neon mixture, which is developed in 1961. Which is nothing but a continuous laser beam. It produces the continuous laser beam. As compared with the ruby laser, it produces the continuous laser beam. Next, characteristics of lasers. These are totally four characteristics are there, Rama, here. Highly directional, highly coherent, highly monochromatic, and highly intense. These are the four characteristics of laser as compared with the ordinary laser source, ordinary light source as compared with the ordinary torchlight source. What are the differences that we can observe here? The first one is high directionality. A laser is a highly directional, which is expressed in terms of divergence. The degree of divergence of laser for laser spots of radii A1, A2 and A1 for the distance of D2 and D1 from the laser source is given by pi equal to A2 minus A1 divided by 2 into D2 minus D1 radians. Okay. The laser beam spreads less than 0.01 millimeter for the distance of 1 meter, whereas searchlight spreads about 0.5 meters for every 1 meter distance traveled, which means that laser is highly directional as compared with the ordinary light source, which is spreading very much smaller values, which is of the order of 0.01 millimeters for the order of 1 meter distance. Whereas ordinary light source spreads 0.5 meters for every 1 meter distance. This is what the comparison between ordinary touch light source and laser source, which means it is nothing but highly directional light source it is. Next, if you look at the diagram here, there are two laser sources. The two sources are there. The first one is incandescent bulb. The other one is laser source. Okay, incandescent bulb spreads the light in all possible directions with all wavelengths. But laser source sends the light in one particular direction with only one particular wavelength. Next, this is another picture of laser source. Next, coming to the next property, that is highly monochromatic. Laser is a highly monochromatic compared to the conventional monochromatic light source of the conventional monochromatic light source because characteristics of nature of stimulated emission process. Because of the stimulated emission process, it produces the highly monochromatic light. What is meant by monochromatic? What is meant by monochromatic here? Mono means single, chrome means color. Single color light will be emitted from the laser source as compared with the ordinary light source. Here there are three cases which are The first one is white light source, second one is monochromatic light source, the other one is laser light source. Okay, in case of white light source, we will limit all the colors, starting from blue color to the other colors. All the colors will be emitted by the white light source. But monochromatic, like sodium vapor lamp, emits the single color light, but uh, it does not travel in a single direction. Does not travel in a single direction, but laser source traveling in a single direction as well as highly monochromatic, okay, which produces a single color light, almost single color light. Delta lambda value is almost negligibly smaller value here in case of laser source. Next, highly coherent. Highly coherent. What is coherence? Coherence is nothing but correlation of phase and amplitude at any point with any other point in the beam of light or waveplane is called as coherence. It's called as coherence. Okay. And to be a coherent source, what are the conditions to be satisfied? What are the conditions to be satisfied? The first condition is the source which the waves which are generating from the laser should have same amplitude, same wavelength, and constant phase difference or zero phase difference. These are the three conditions should be satisfied by the coherent source. To be a coherent source, it should have same amplitude, same wavelength, and zero phase difference or constant phase difference. Constant phase difference. Next, coming to the next property, that is high intensity. Laser is highly intense source. This is due to the This is due to the high coherence and high directionality. To other properties, due to the high directionality, intensity decreases very slowly due to the coherence amplitude gets added up. If A is the amplitude of the single wave train and N is the number of coherent sources, then the intensity is given by I equal to N square into A square. N square into A square. This is what high intensity. Next, interaction of electromagnetic radiation with matter. What are the quantum processes which takes place inside the material medium when electromagnetic radiation interacts with matter? What are the quantum processes which takes place? First one is absorption transition. The next one is spontaneous emission transition. The third one is stimulated emission transition. The first one is absorption transition, also called as stimulated absorption transition. Next one is spontaneous emission transition. Next one is stimulated emission process. These are the three processes which takes place inside the material medium, inside the laser medium. To produce the laser medium, these are the basic transition which we have to know. The first one is absorption transition. In the case of absorption transition, what is happening? The atoms in the ground state absorb the photon energy and go into the excited state. This is called as absorption transition. In this particular process, one photon will be absorbed by the atom and going to the excited state. The atom is going to the excited state. And then next, spontaneous emission process. What is happening to the spontaneous emission process? In case of spontaneous emission process, the atoms in the excited state will not stay forever in the excited state. There is a lifetime for the excited state, and that particular after the lifetime of the excited state, it will come back to the ground state or lower energy state by releasing the X amount of energy, by releasing the absorbed photon energy. This is what spontaneous emission process. This is called as spontaneous emission process. Okay, now after the 10 to the power of minus 9 seconds, the atom will come back to the ground state by releasing the absorbed photon. One photon is absorbed, one photon is coming out from the material. One photon is coming out from the atom. This process is called as spontaneous emission process, and this process takes place inside the ordinary light sources. Ordinary white light source, sodium vapor lamp, mercury vapor lamp, etc., etc. Next one is stimulated emission process. In case of stimulated emission process, one photon hits the one atom in the excited state, releases totally two photons. One photon is the induced photon, the other one is the absorbed photon. One is the induced photon, the other one is the absorbed photon, due to which two photons released at a time from the atom, which satisfies the coherence condition. Coherence condition means same amplitude, same wavelength, and zero phase difference, constant phase difference or zero phase difference. Okay, satisfied by the coherence condition. Okay, and these two photons hits another two atoms in the excited state, releases totally four photons. Again, those four photons hits another four atoms in the excited state, releases totally eight photons. Like that, photons multiplication will be taken place. Avalanche multiplication of photons will be taken place here. Okay, so that intense laser beam will be comes out from the material which satisfies the all the special characteristics of laser, like high directionality, high intensity, high monochromaticity, high coherence. All these properties will be satisfied by the bunch of photons, those bunch of photons. These were the interaction of electromagnetic radiation with matter. These are the quantum processes which takes place inside the material medium when the electromagnetic radiation interacts with the photons. Electromagnetic radiation interacts with the atoms or material or electrons. Anything you can take it. Atoms means inside the atom there will be electrons. Photon absorbed by the atom means photon absorbed by the electron only. Okay, in terms of electron representation also you can understand the same thing. In terms of atomic representation also you can understand the same thing. Next, coming to the next one is Einstein coefficients. Einstein coefficients in case of stimulated absorption process, in case of spontaneous absorption, spontaneous emission process, in case of stimulated emission process. There are three cases. In these three cases, what are the Einstein coefficients that we are going to discuss here? It is a process of excitation of atom into the excited state from the ground state by absorbing the incident photon. This is called as absorption process. This is called as induced absorption process. Because of the external stimulation, the absorption process is taking place. The atom is excited into the excited state. It's not going by itself, but it is because of the external photon, it is going to the excited state. This is called as stimulated absorption process. We are giving the external stimulation to the atom. Now these are the two states, ground state energy state. The other one is excited state. From the ground state to the excited state, the atom is going. Okay, this is called as stimulated absorption process. In this particular process, this stimulated emission process, stimulated emission absorption rate is directly proportional to the number of atoms in the ground state. More the number of atoms in the ground state, more the absorption transition that we can observe here. More the number of atoms in the ground state, more the excitation of atoms. Because of this, absorption rate will be increased. Next one is the energy density of the incident radiation. Energy density of the incident radiation also one of the parameters which rules this particular process. Okay, to increase the number of photons, density of the photon. If you increase the density of photons, what will happen? Again, this particular process also increases and more and more. That is what another parameter. Or you can write down this one as B12 into rho of nu multiplied by N1. Rho of nu multiplied by N1. This is what the equation. In this particular equation, B12 is nothing but known as Einstein coefficient for the stimulated absorption transition. Einstein coefficient for the stimulated absorption transition. Stimulated absorption transition. Next, spontaneous emission process. It is the process of de-excitation of atom itself into the ground state after its lifetime from the excited state by emitting the photon. Okay, this is a process by itself. The atom is coming back to the ground state after 10 to the minus 9. After 1 nanosecond, it is coming back to the ground state by itself. We are not giving any external stimulation. We are not giving any external stimulation to the excited atom. By itself, the atom is coming back to the ground state. This is called a spontaneous emission process. Okay, in this particular process, this rate of spontaneous emission process depends only on the number of atoms in the excited state. That is nothing but number of atoms N2. N2 is the number of atoms in the excited state, which depends only on the one particular parameter that is called as number of atoms in the excited. It does not depend on the instant radiation. It does not depend on the energy density of the instant radiation. Energy density of the instant radiation depends only on the number of atoms in the excited state. So we can write down this expression as A21 multiplied by N2. A21 multiplied by N2, where A21 is nothing but known as Einstein coefficient of spontaneous emission. Einstein coefficient of spontaneous emission process. Okay, now next one is stimulated emission process. Stimulated emission process. In this process of de-excitation of atom into ground state from the excited state, interacting with additional photons with itself. This is called as, next one is stimulated emission process. In this process of de-excitation of atom into the ground state from the excited state by interacting with additional photon within its lifetime of within lifetime of excited state by emitting the additional photon. Within the lifetime of excited state, the atom will come back to the ground state because of the induced photon. Because of the induced photon, one more external photon collision with the external photon, this particular atom is coming back to the ground state by releasing the two photons. One is the absorbed photon, the other one is the emitted, another one is the induced photon. Two photons are coming out from the atom at a time. And this is what stimulated emission process. And this particular process depends on the two parameters again. The first one is number of atoms in the excited state, that is number of atoms in the excited state, that is nothing but N2, and also it depends on the energy density of the instant radiation. If you increase the energy density of the instant radiation, automatically this process also increases. Okay, these are the two parameters which rules this particular stimulated emission process. Okay, and this equation can be written as B21 N2 rho of nu. Okay, where B21 is nothing but known as Einstein quotient for the stimulated emission process. Einstein quotient for the stimulated emission process. Next one is population inversion. What is population inversion? The number of atoms present in the excited state N2 is greater than the number of atoms present in the ground state N1 is called as population inversion. And before going to the population inversion, what is normal population? At thermal equilibrium, the number of atoms in the ground state is almost always greater than the number of atoms in the excited state. Okay, at thermal equilibrium condition. This is what the first case N1 greater than N2 greater than N3. N1 greater than N2 greater than N3. Okay, the number of atoms, these are the number of atoms on x-axis, and y-axis are taking energy. Okay, number of atoms are slowly increasing and increasing here, slowly decreasing and decreasing here as you keep on increasing the energy value. Okay, now N1 greater than N2 greater than N3 at thermal equilibrium condition. But when the population inversion is achieved through the different mechanisms, what will happen? The number of atoms in the ground state is less than the number of atoms in the excited state. This is what the condition, N2 greater than N1. This is called as population inversion condition. And this population condition is required for the more and more stimulated emission process. To trigger this stimulated emission process, we need this population inversion condition. Number of atoms in the excited state should be greater than the number of atoms in the ground state. That condition has to be satisfied to get the stimulated emission process. To dominate the stimulated emission process, then compare with the spontaneous emission process, we need population inversion. Next, one more condition is that is metastable state. One more condition which is required for the this particular stimulated emission process. We need metastable state. Okay, what is metastable state here? If there are only two energy states, stimulated emission of radiation is not possible. Okay, stimulated emission process is not possible with the two energy state. One is the ground state, the other one is called as excited state. With two energy states, the population inversion or stimulated emission process does not takes place. Okay, to get the stimulated emission process, we need at least three energy states. At least three energy states are required to get the stimulated emission process. To get the lasing action, we need three energy states are required. Minimum of three energy states are required here. Okay, now for stimulated emission, there must be at least three energy states rather than two energy states. Okay, these states are known as metastable state. This state is known as metastable state, where the lifetime of this particular state is 10 to the power 1 milliseconds to 1 microsecond. 1 milliseconds to 1 microsecond. Okay, this is called as metastable state. Okay, that can be located in between the ground state and the excited state. In between excited state and ground state, this particular energy state is located. This is called as metastable state, which is having longer lifetime compared with the ordinary excited state. It is having longer lifetime compared with the ordinary excited state. This is called as metastable state. Okay, at this particular metastable state, more and more number of atoms will be accumulated, so that such a way that population inversion will be achieved between the metastable state and the ground state. And this is what the metastable state definition and importance. Next, coming to the next one is pumping methods. And before going to the pumping methods, first we have to discuss there are 3-level energy scheme and 4-level energy scheme. In the case of 3-level energy scheme, what is happening and what is happening in the case of 4-level energy scheme? First, look at the 3-level energy scheme. What is happening? There are 3 energy levels are there among here: E1, E2, E3. E1 is the ground state energy level or low energy state energy level. And then next one is E2 energy level, which is called as metastable state. The other one is called as pumping state. The exact almost E3 energy level is called as pumping energy state. Okay, now from this particular E1 energy level to the excited state, this particular pumping transition will be taken place, so that energy atoms will be excited to the excited state, that is called as pumping energy state. And then from there, rapid radiationless transition will be taken. Radiationless transition will be taken. Within no time, radiationless transition will be taken place, and these atoms will come back to the metastable state. Will come accumulate at the metastable state. Okay, now this is called as metastable state. At this metastable state, more and more number of atoms will be accumulated. Once population inversion is achieved between the metastable state and the ordinary, the ground state energy state, the stimulated emission process takes place here. That is what you can look at from the other diagram. There are two atoms in this particular state. There are many atoms compared with the ground state atoms. Once this population inversion is achieved between these two states, ground state and metastable state, stimulated emission process triggers the spontaneous emission process. Okay, within no time, bunch of photons released from the this particular stimulated emission process. Okay, and this stimulated emission process in this particular three level energy scheme will get a pulsating laser beam. We will get a pulsating laser beam rather getting a continuous laser beam. We will get a pulsating laser beam, because to get the population inversion, it requires some time. Okay, the atoms has to go to the excited state, and then from the excited state to the metastable state, the atoms has to accumulate. Okay, atoms has to be accumulated here. Okay, because the ground state is having almost infinite lifetime, we have to get the population inversion between the ground state and the excited state. That is a difficult job. Okay, that is a difficult job. To get the population inversion, it requires some time. So bunch of photons released at a time. After that, again some time, and then again fraction of seconds, again bunch of photons will be released. Like that, bunch and pulsating laser beam is coming from the 3-level lasing system. That is what happening in the case of 3-level lasing system. Next one is 4-level energy scheme. 4-level energy scheme, what is happening here? There will be 4 energy levels. Instead of 3 energy levels, there will be 4 energy levels. Level 1, level 2, level 3, level 4. E1, E2, E3, E4, N1, N2, N3, N4. Now, in this particular case, pumping transition will be taken place, followed by the radiationless transition. And then here, this particular level, population inversion will be achieved between the two intermediate energy level. Two intermediate energy levels, you are getting the population inversion, not between the excited state, not between the metastable state and the ground state, but between metastable state and other ordinary intermediate states. Okay, now between these two states, they are getting the population inversion. Okay, now this population inversion will be taken place within no time, because the population inversion is between two excited states, not between the excited state and the ground state. Because of that, even a very small number of atoms are enough, to get the population inversion. Even larger number of atoms are enough to get the population inversion between the two excited states, because this particular energy state doesn't have any atoms. Almost nil atoms are available at this particular excited state. So what will happen here? It is the population inversion is easily can be achieved between the ordinary excited state. So we will get the continuous laser beam from the 4-level lasing system. As compared to the 3-level lasing system, we'll get the pulsating continuous laser beam in the case of 4-level lasing system. 4-level lasing system. Next one is pumping methods. What are the pumping methods here? There are totally 5 pumping methods are there, depending on the laser, that depending upon the active medium or depending upon the laser medium, where the totally pumping methods are 5 types of pumping methods are there here. First one is optical pumping method. Optical pumping method means we are sending the optical energy. Light energy will be directed to the transfer to the active medium. That is called as ruby rod in case of ruby laser. In case of ruby laser, ruby rod, we are supplying the optical energy to the active medium. That is called as ruby rod. Okay, next one is electrical discharge method. Electrical discharge method, what we are doing here, we are sending discharging the electrical energy into the gas discharge tube, so that energy will be transferred from electrons to the helium atoms or neon atoms, so that excitation and de-excitation process will be taken place, so that you'll get the laser beam. Okay, now next one is direct conversion method. Direct conversion method takes place in case of semiconductor lasers. In case of semiconductor laser, direct conversion will be taking place. Direct conversion method means directly electrical energy. Because of the direct electrical energy, electrons and holes will be recombined with each other. Because of the recombination of electrons and holes, for light energy will be emitted from the material. Light energy will be emitted from the material. That is called as laser light. Next one is due to the chemical reaction. Due to the chemical reactions, energy will be released. Huge amount of energy released from the chemical reactions. That released energy will be used for the excitation and de-excitation processes. Okay, that is called as chemical reactions method. Next one is inelastic collision. Inelastic collisions between atoms. Inelastic collision between atoms. What is happening here? The collision will be taking place between the atoms. Because of that, one atom transfers the whole its energy to the another atom, so that this particular atom will go to the excited state. Okay, this called as inelastic collision between the atoms. Okay, in this particular process, only momentum will be conserved, energy will not be conserved. That is called as inelastic collision between the atoms. This particular process will be used in the gaseous lasers. Again, will be used in the gaseous lasers along with the electrical discharge method. Along with the electrical discharge method, this method also will be used to get the excitation and de-excitation process. Next one is types of lasers. There are totally different types of lasers are there, Amma. Different types of lasers are there. The first one is solid state laser. Also, solid state laser. Examples are ruby laser, ag lasers. Next one is gaseous lasers, carbon dioxide laser, argon ion lasers, helium laser, etc. etc. Next one is liquid lasers, europium chelate laser, silicon oxygen dichloride laser. Next, dye lasers. Next one is dye lasers, rhodamine 6G laser, formalin dye lasers. Examples for the dye lasers. Next one is semiconductor lasers, indium phosphide laser, gallium arsenide lasers. These are the examples for the different types of lasers and different examples given for the different types of lasers. Totally 5 types of lasers are there: solid state laser, gaseous laser, liquid lasers, dye lasers, and semiconductor lasers. Okay, these are the different types of lasers and given the corresponding examples. Corresponding examples are given here. Next one is main components of lasers. What are the main components of lasers here? The first one is active medium, energy source, optical resonator. When the active medium is what is active medium here? When the medium is excited, it achieves the population inversion. Active medium is the medium where all the laser transitions are taking place, like absorption transition, stimulated emission transition, spontaneous emission process. Okay, the active medium is a medium where the lasing action takes place. Where the lasing action takes place, population inversion will be achieved, and all the process takes place inside the active medium only. Next one is energy source. What is energy source? The energy source rises the system to the excited state, okay, which has nothing but a pumping source. They are pumping the energy to the active medium. Like different pumping methods we discussed just now: optical pumping method, electrical discharge method, chemical reactions. Due to chemical reactions, inelastic collision between the atoms, direct conversion method. Different methods are there to send the energy to the active medium. That is what energy source and a pumping method. Next one is optical resonator. What is the purpose of optical resonator? It increases the intensity of laser beam. It increases the intensity of the laser beam. That is what the optical resonator purpose. It contains mainly 2 layers. Contains mainly 2 components here. The first one is fully reflecting mirror. The other one is partially reflecting mirror. This one is called as fully reflecting mirror. The other one is called as partially reflecting mirror. Okay, between these 2 mirrors, whatever the photons which are emitted from the active medium will be reflect back and forth, so that more and more stimulated emission process will be triggers, and more highly intensive beam will be comes out from the material, from the partially reflecting mirror. This is what the purpose of optical resonator. Next, these are the